Screen sharing is visible to all. Okay. So Monday we are discussing about buoyancy and its phenomena and what is meaning of buoyancy point and center of gravity of the body. Today we'll discuss about just a minute. Yeah, today we'll take some more examples on buoyancy and other discussions. And later, if possible, we'll start with the metacentric height. Okay. So coming back to the buoyancy problems, the next problem is a stone weighs 392.4 newtons in air. Okay, so normal weight of the stone, which is weighed in the atmosphere, is 392.4 newtons. Same stone, which is weighing 196.2 newtons in water. So as we discussed, the buoyancy force is going to resist that sinking of the given bodies, and after that resistance of the buoyancy force, which is opposing the normal weight of the stone, so that weight is 196.2 newtons in water when it is sinking. Compute the volume of stone and its specific gravity. See here, for the volume of stone, we don't know any dimensions of the stone also. I hope you are understanding. Dimensions, if anything is known, we would have found out the volume directly by the standard dimensions of the standard formula. And here, also we need to find out specific gravity. All of you can recall what is the specific gravity ratio. Can anyone tell me what is the meaning of specific gravity? How we can find out for the given stone? Until now we see specific gravity of oil in the manometer, specific gravity of the mercury or specific gravity of the water. But here they are asking specific gravity of stone where only weight is given or difference of weight is given. What is specific gravity? In very early classes of the properties of fluids we have discussed specific gravity of the substance or the specific gravity of liquid. Any reply?
So it is ratio of density of the stone upon the density of water.
Yes, very good. So specific gravity of any given substance, we are taking density ratios. So density of the given body to the density of the standard liquid. So that standard liquid we are considering water. So as per this given object here, we are having stone here, and with respect to stone, we have to take the ratio of density of water. Then we can find out the specific gravity. Means in this problem we need to find out densities first. Water density, all of you know. Density of stone is not known, and to find the density, we know the units of density. So go by units. The unit of density is what? Kg per meter cube. Correct? So kg per meter cube means what? Kg is the mass, but here weight is given. So convert this weight into mass. So mass in kg per meter cube. Meter cube is volume. So volume per meter cube anyhow we are taking. We don't need the volume value. Okay. So once the density of the stone is known, by converting this weight into mass, one can go for finding the specific gravity. And here, other than mass, weight, and specific gravity, volume of the stone is also asked. So that volume of stone, we can go by buoyancy law itself. So by the law of buoyancy, what we know is any body, if it is uh, tried to immerse in a given liquids, it will replace the liquid by its own volume. I hope you are understanding. Once I put any body in the water or any liquid, it will replace the liquid of its same volume. Okay. and that volume or the weight of the stone, how much it is there, we are going to take the same weight which is displaced by the stone equal to weight of the liquid displaced. So here now coming to the equilibrium state, because here as stone is told, we all know that it will start sinking and it will move on up to the bottom position. But until that, we need to consider one of the position. Okay, one of the position is what we'll consider at any given instance at equilibrium, the net weight of the stone. Now weight of the stone is also not given here exactly. Why? Because weight of the stone in different liquids is different, or different fluids it is weighing different quantity. So for that, what they have done is they have taken difference of weights. So how much it is exactly actually weighing in air and how much it is weighing in water. So that difference of weight will be nothing but weight of the water displaced. Okay. So if they are considering that one, you can see here now difference of weight is what? The weight in air and weight in water. So this difference of weight, how much it is there, that much volume of water will be displaced, or that much weight of liquid will be displaced in the container. Okay, so taking this difference, we'll get the effective weight of the stone when it is just sinking in the water. So that effective weight is nothing but weight of the liquid displaced. So for the weight of the liquid displaced, one can find out by rho g v value that we have considered for the buoyancy law. So weight of the liquid we can find out by taking density of the water, g value, and the volume of water displaced. Now in this all numbers, we don't know the volume of the water. So once we know the volume of water, how much it is displaced, because volume of the water also, if you tell whether it is in trapezoidal shape or whether it is a hemispherical or a spherical shape, we don't know. It is uneven stone, uneven surface or uneven volume. But we know the value in meter cube. That we can find out by this equilibrium position. So after substituting these values, volume of the water, whatever is displaced, that is nothing but the volume of stone itself. So that volume is around here, it is coming around 2 into 10 raised to 4 centimeter cube. So if you want to find out in other units, you can find out it. So 2 into 10 raised to 4 centimeter cube it is. You can assume any shape of the given volume of liquid or volume of stone. Okay, same volume of the stone, that volume is now replaced. The stone is replacing the same volume of liquid also in the container. So we are assuming this volume of the liquid is nothing but volume of the stone itself. So volume of the stone is also 2 into 10 raised to 4 centimeter cube. But mass, weight, and other properties or the densities may be different. But the only volume we are considering, volume is equal. Then we are coming back to the specific gravity. So volume we know, you can write here, volume of the liquid 2 into 10 raised to 4 centimeter cube equal to volume of the stone 2 into 10 raised to 4 centimeter cube. Now as I told you, you go by given weights, convert that into mass. So mass of the stone, if you find out, because specific gravity we are taking for the ratios of the densities. So we need to find out only density by using the mass. So mass, which mass you have to consider, water or air. Normally we take all the weights with respect to air, which is in the air. So that air weight is how much? 392.4 is given in the problem. Okay. Then you have to divide by 9.81. You will get the mass in kg. So stone is weighing 40 kgs. Or if mass is given, you can convert it into weight also by multiplying g value. And once this mass is known, then we can go for the finding density. So density is kg per meter cube. So take the ratio of that values. So mass per unit volume. So mass per unit volume, mass is 40 kgs. Volume, you can convert this into meter cubes because we need answer in kg per meter cube. So per meter cube, how much is the density that you can find out for the stone. So all of you check these values. Volume, is it coming with this value 1 by 50 into 10 this meter cube? Just check. 2 into 10 raised to 4, same volume for the stone also we have considered. So whether in meter cube, is it 1 by 50 or what value it is there, you tell me. How much is in meter cube volume?
Excuse me, sir.
Yes.
Sir, we're supposed to calculate volume only.
Yeah.
Sir, we should calculate volume only, right?
Volume of,
Stone.
yeah, volume of stone.
And how did
That's
you get that 1 by 50?
that's what I'm asking you. Convert this 2 into 10 raised to 4 centimeter cube in meter cube. How much you are getting? You that tell the value.
Okay, sir.
Don't take 1 by 50. That's what I'm telling you. I have written here 1 by 50. Whether you are getting 1 by 50 ratio is same with respect to 10 raised to 4, 2 into 10 raised to 4 centimeter cube in meter cube, whether both values are same. That you check.
Sir, 0.02.
0.02
02.
meter cube.
Yes, sir. That's so 1 by.
Okay. That is also 1 by 50. Okay, if it is 1 by 50 only, you can
Yes,
take
sir.
0.02. So all of you write down mass is 40 kg, volume you write down 0.02 meter cube. 0.02 meter cube and find out what is the value of density of the stone. So I think all of you are getting 2000 kg per meter cube for the stone. Okay. Now, once you know the density of given object, now we will take the ratio of density of stone to the density of water. So all of you know the standard density of water, that is 1000. So we'll directly divide that density of stone by density of water. Why? Because we are finding specific gravity of the given stone. If it is specific gravity of water itself, then we would have taken ratio of density of water to density of water like that. But here stone is given, so I'll take 2000 by 1000. It will be 2. So all of you can note down this procedure and note down the answers. Shall we take next problem? Okay. So next problem we note down. A stone is floating. See here. Now this is a different example which is floating here. Stone is floating at the interface of mercury and water such that 35% of its volume is in mercury and 65% in water. Calculate the density of the stone. So in this example, an object is floating in the given interface of the liquids. Okay, between interface of two different liquids, it is floating. So where mercury and water both are given. So as per general observation, mercury is having higher density than water. So for our understanding, we'll take mercury at the lower level because of the higher density. And above this mercury, water is kept. And in between this interface between water and mercury, a stone is there. So that stone is balanced. The weight is balanced by this mercury and water by different percentages. 35% of its volume, okay, 35% of its volume is in mercury, means lower side. 65% of volume is in water, in the upper side, because water density is lower. And we also know that water and mercury will not mix, so that there will be interface can be created easily and stone can be floated in between. Now in this problem we need to find out, calculate the density of the stone we need to find out. So again you can recall the earlier problem. You can find out the volume displaced by stone, volume displaced by the liquid because of the stone here, and that total volume of the water as well as mercury, how much it is displaced, that total volume will come to the volume of the stone, because stone is separated by two interfaces. 65% is in water, so 65% mass, that weight of the volume of the stone is replacing water particles, and 35% what is shown here at the bottom here at the stone bottom side, 35% of this stone volume is replacing some of volume of the mercury at the bottom side. So taking that again, the force applied by the given stone, the effective force applied, you can consider. So all of you again apply the buoyancy law. The total weight of the given stone. So weight of the stone is not given here, but indirectly we have told the weight of the water we can find out. Water and weight of the mercury, how much it is. Then we can equate to the total weight of the force developed by this buoyancy. So total weight acting by the stone is supported by mercury as well as water here. So both are added here, and percentage of volume is given, not the exact value. So by this directly they are finding the density. One more method is you go by the volume. You can take the total volume, and same volume you can tell with the volume of the stone also. So by this relation, can we find the volume exact value? Once you know the density, can we find out the volume of the stone? Check the volume also. So substitute density back to the initial equation. And
Sir, 1.88 10 raised to minus 5.
1.88 in 10 raised to minus 5. Minus 5 volume of the stone. Point 999 meter cube.
Yes, sir.
Okay. So also try that method to find the volume of the stone, or a total volume of the fluid displaced. Okay, total volume of the fluid displaced, both water as well as mercury. How much volume is displaced, or how much volume of stone is occupied in the interface. That also you can find out. Okay, now we'll move to the other problems or the other concepts. So earlier also we discussed about stability of floating bodies. So here stability means a body which is floating in the given liquids or which is in the submerged surfaces in suspended positions. In such conditions, it should be remaining in the same position after any movements given to the body. Or if any movements of the couple is generated on the body, it should come back to its original position. So such type of method or the principle where the restoring of the unstable bodies to the stability is called as the floating body stability. So here, if a body is not homogeneous in its distribution of mass over the volume, then this instability will exist. And many times we assume all the bodies are isotropic material. Throughout the material, the properties are same. That is one of the assumption. But many objects, if you see, the mass is not constantly distributed. So sometimes the mass is focused, or the more mass is on one side it will be lightweight because of the irregularities of the distribution of mass and other things. So there exists the instability of the given bodies. And the location of this gravity as well as buoyancy point also very important. How it will depend and how it will vary the stability of the given bodies. So this we'll see in the examples here. So in this first example, we can take the point of buoyancy above center of gravity. So assume this section of a ship here, or a section of any solid body which is just floating or just touching the surface of the water, or it is floating. In such cases, if it is floating or just touching the surface of water, we assume that whatever the buoyancy force is developed by the liquid is equal to the weight of the given body. Then only it can float. If cannot float, whenever we call about the sinking bodies or the higher density materials, it will sink. Then what will happen? Weight will be higher and buoyancy force will be less. In such cases, the body cannot float or body cannot suspend in a given liquids. It will sink to the bottom. So first one example, if you see, considering the buoyancy point just above this center of gravity point. So whenever a couple is generated, because whenever these bodies move in liquids or float on the liquids, there will be difference in moments. Say for example, on right side or left side, because of the different weights on the ship on right side or left side, there will be slowly some couple will be generated. And even while propelling or stopping the bodies, what will happen? The front and back side movement will be generated. Yes or no? So similarly here, in this example also, a moment is generated about this axis. BG axis, if you take one axis between weight and that buoyancy force, one line if I consider vertical axis. In the front view, I can see the movement about this axis in right and left direction because of the difference in weights, or while stopping and propelling, or even with the different loads on the front side and back side of the ship. If you see, there will be again some couple will be generated, or the moment will be generated about the center axis. And the loading and unloading of the ships, if you see, the loading and unloading of the ship is done from the center, not from the corners of the ship. Because what will happen? Because it is floating on the water, you cannot load the ship on one side or only on the front side or only on the back side. So later what happens? These moments will be very high. Then this couple whatever is generated because of the high loads on one of the corner of the ship, then there may be sinking or instability of the ship will be prepared, and it may sink in any given time. So loading of these type of bodies should be made equally from all the corners, so that we can start from the center and we can equally distribute all the loads. Like say for example, you can assume the containers which are loaded on the ship. So slowly from the center they can plan what is the load in the entire ship in each corner, what is the load is acting, or how much load is applied from the external loading. So keeping that in mind, they can load from the center and equally they can distribute the loads, so that equilibrium is achieved, or the stable equilibrium is achieved in entire travel or the trip of the ship. So it should not have any unstable conditions. So in this condition, if you see, whenever if I apply for experimental purpose, I will not apply any loads here. I'll just apply one couple here or any moment on the left side or right side. So because of this difference, what will happen? This body will start moving about the axis or about the point B. It will start rotating by some angle. Then after some time, it will come back to its original position. So this is possible when the G is below B or B is above G. Or can keep in mind, where is the center of gravity? Center of gravity, if it is lower than the center of buoyancy point, then the body is always stable. Whatever the couple you apply or whatever the movement you give, any movement is possible. Later, after some time, it will retain its original position because of the lower point of this G. So always for such floating bodies, we have to maintain the center of gravity below center of buoyancy. Okay. Then one more case you can see, unstable equilibrium, where B is considered below G. In such cases, Okay. So this case, what you can assume, always W is equal to FB is okay. But what will happen here is, when point B, buoyancy point is lower means, see here, volume of the liquid, center of the volume of liquid itself is the buoyancy point where the force is acting. So such bodies will be floating very high from the bottom surface. Or you can take this condition where center of gravity is very less, buoyancy point is very high. Means what will happen? This surface, top surface is very near to the liquid surface, or it will be floating such that maximum part of the body is inside the liquid. So the stability will be more. It should not float with very low level of water. Just for notation, we have shown the water level above these surfaces. But in such surfaces, what will happen? If the center of gravity is above center of buoyancy, any couple which is applied on right side or left side or moment is applied, it cannot restore back to its original position. So because of the center of gravity, it may fall down on right side or it may fall down to the left side. It cannot retain its own position. So such type of couple we are calling it as destroying couples, which are not the restoring couples. So this condition is possible when center of gravity position is above the center of buoyancy point. Okay. Then last is neutral equilibrium. In neutral equilibrium, what we are doing, we are considering both the points on the same position. Okay, both the points on the same position. This is possible when the bodies are just touching the water surface. Why? Because the center of buoyancy, the volume of liquid displaced, that center is also same. Then the center of gravity of the body is also lying on the same point. In such cases, it is like a suspended body. If you give any couple, it will be retained in the same position. Means not in the original position. Whatever the couple is given on right or left side or front or back side, the magnitude of the couple decides the change in the position of this body. So once the couple is given on right side or left side, it will retain the applied couple, or after applying the couple, it will go to that position and stay for a long time. It will not come back to the original position, or it will not try to destroy the couple also, or it will not try to fall down also. It will be like a suspended body. So any rotation if you give, it will rotate and keep on in the same position for a long time. So this type of condition is called as neutral equilibrium. This is possible if the bodies are designed with same center of gravity and same buoyancy point. Okay, if there is no difference between G and B point, then such bodies will be having rolling type of couples, or we are calling it as neutral equilibrium. It will not come back to original position, or it will not even fall also. So how much couple is applied, according to that it will rotate and stop there. Any doubts here? So we discussed stability of the bodies with respect to buoyancy point and the center of gravity. Later again we are discussing these positions of buoyancy point, center of gravity of the body, and metacenter also. But first thing to understand is always the center of gravity should be below the center of buoyancy point. Then only maximum bodies will be having a stable condition in any type of couples applied, or it may come back to the original position even after applying the moments about this axis. So this is more preferred. And center of gravity, if it is more than above the buoyancy point, such bodies are not preferred for the stability in the given floating conditions. Okay, we'll go to the next point. Yes. So next is metacentre and metacentric height. So again, from the buoyancy forces of the buoyancy phenomena, we are describing one more entity called as metacentre and metacentric height. So for example, you can consider any body here of any shape. So for our reference, we have considered one rectangular type of object here in the front view, which is having point B below here, point G is above. That depends. That depends on different bodies. You can ask me, sir, you told just now the point G should be always below and B should be above. This is for a reference, for derivation or for reference of explanation I have taken. So as per our consideration, this body is now it is in unstable equilibrium. Yes, unstable equilibrium only. Then this GB point you can consider in any type. You can consider either on the same point, or B you can consider above, and G you can consider below also. Depends. But for maximum times, for the unstable bodies only, we are calculating the metacentric height and metacentres. Because whenever this instability is possible because of the buoyancy and center of gravity forces, we will try to balance them. We will try to balance the destroying forces or the destroying couples by considering this metacentric point. Okay. So what is this metacentric height? How it is calculated? Okay. How it is found out? How it can be balanced so that the stability in the body can be retained. So this we are discussing in these topics. That's why we have taken G just above the buoyancy point, assuming the body may be unstable. And as we know, the weight of the body is acting downside, then force due to buoyancy force is acting upside in the equilibrium. Then for finding the metacentric point, we are taking one couple here, or we are applying some moment about this axis. Okay, or about the point B. So once you apply any moment about the point B, it will start rotating. So once it rotates, the new axis you can observe here. New axis is what? M to B dash. So it is moving from B to B dash once you apply any couple. So here couple is applied on the right side as per the given sketch here. Right side couple is applied. Maybe because of stability, it may be having restoring couple, or with respect to unstable conditions, it may have the destroying couple also. But for derivation, we have to take restoring couple. This is very important. If you take destroying couple, then there is no meaning of finding the metacentric point. So we need to find out for the restoring couple what to be done. So we assume some restoring couple should be generated inside this, and you can see here there is a displacement between weight of the body, that is WG line. This line is displaced from the axis of BM, and force FB, the buoyancy force, is acting in some other different point. So because of this, the instability of the couples will be generated. Is that clear? Now how much couple is given, that is shown by this theta. The tilt position of the angle of couple, that we can find out by this theta. So it is tilted by theta angle, and the intersection of this initial line or the vertical axis to the tilted axis. If you see the intersection of these two axes, BM and B dash M, those lines will meet at M, and this point is called as metacentric point. Okay, so at this point we are going to decide whether it is going to be stable or not stable. So this can be understood in the problems. When we solve the problems, we can understand how this metacentric point is going to affect the stability of the given bodies. You can observe here the line of action of buoyant force B1 intersects the vertical axis at M, called as metacentre. So this is the metacentric point. All of you taken the sketch? Now we'll try to find out this position of the metacentric point from GM or from BM as per this sketch, as per the sketch given here. Now for that, you can note down the different names here. So G to M, we are going to call it as metacentric height. Center of the distance between center of gravity to the metacentric point is the metacentric height. And the distance between buoyancy point or the center of the buoyancy to the metacentric center, the distance is called as metacentric radius because it is rotated about B as per this sketch. Okay, this is the metacentric radius. About this, it is going to rotate. And G to M is metacentric height. So whenever you solve the problem, whether if G is below B also, G to M, we are calling it as metacentric height. And if B is above G also at this point, say for example B is near to M, so B to M we are calling it as metacentric radius. Okay, so metacentric radius is what? The distance between buoyancy point and the metacentric point. The distance between center of gravity, any position on this side, any position center of gravity, any point if you consider, from that point to the metacentric point is the metacentric height. So from that sketch, we'll analyze the sketch once again in the top view, front view, and other things after applying the couple. So here, if M is above G, see here, for the bodies with metacentric height, if you see, if the metacentric point is above G, then it is stable. If M is below G, it is unstable. And if M coincides with G, it is neutral. Similar thing again. So again, you can recall, if M coincides with G and G coincides with B, it is completely neutral equilibrium. Any couple applied to the body, it will go to the new position, it will remain for long time. Until and unless you apply any reverse couple or the forward couple, it will be in the neutral position. So for, again, some more stability, this metacentric height is very important. So in any unstable bodies where G is above B also, in such cases, we can have the metacentric positions. So metacentric position is nothing but once you try to apply extra load on the body, like in the ship is not only, empty ship is moving in the reverse of the sea. We are going to apply some extra load. So those loads, once it is applied with some couples, it will decide some metacentric point. At what point it is going to tilt, or at what fixed point it is going to tilt, that point should be above center of gravity. So if that metacentric point, if it is above G, then the body is stable. It cannot fall down, or it cannot sink, or it cannot be neutral positions. It will come back to its original position. After any type of couples applied, it will come back to its original position. That equilibrium we need. So I'll just analyze the same sketch in the front and top views here. So about stability, we'll see the problem so that you will understand in more detail in the problem. So in this sketch, so in the syllabus we have theoretical or analytical method of finding the metacenter height. Experimental method is in the lab. Fluid mechanics lab, we are doing the experimental method by applying some load for preparing the couple, and some other method is followed there. Here we are following the other method in the theoretical or analytical method. So this is there in the syllabus. So just analyze this in the front and top view. So stop the class here. Okay, we'll have the break. Again at 11 we'll come back. Okay. Yes, we'll continue the class. Again, check the screen sharing and the audio. If any network issue is there, please report. We'll continue. Okay. So we are discussing about finding the metacentric height by taking one of the example. So this body is floating on the given liquid surface. So in the front view, we have taken this like a rectangular shape, and in the top view, we have considered for a given length of the body. So this is the small thickness what you have considered here, dx for a given length. So length is shown here, total length, and the distance between or the width of this body is x here, or from the center it is taken as x up to given position, or other side you can consider one more x distance from the center. So 2x total, if you take from center, 2x will be the total width of this given body. So x from both the sides, if you consider, the width of the body will become 2x. And for this body, if you see, if you try to apply some small moment, okay, so this is the central axis. Initially, on this central axis, without any disturbance, the body was stable and it was floating on the surface. Now, while moving, if any small tilt is given, or small couple is given, or the movement is given about this point A, M, what will happen? There will be movement or sinking of this part on the right side. Some part, extra part will be sinking on the right side. Some part of the body on the left side will be lifted up. If I tilt it on the left side, okay, if I tilt on the left side, as per the screen, left side if I tilt, what will happen? Some part, some triangular type of shape will be immersed on the left side, and some part of this triangular shape will be lifted above the liquid surface. Yes or no? So similarly here, for example, we have taken right side. Right side after tilting, what will happen? This shape, this triangular shape, as per the given sketch, it will be immersed. Extra immersing will be happening on the right side. On the left side, it will be lifted up from the submerged liquid. This part of the body is lifted up. And after tilting, the buoyancy point, actually earlier it was at B. Now the new position, because more mass is inside the liquid on the right side. Very small of the less mass is submerged on the left side. So what will happen? The buoyancy point will be shifted from B to B1 because of the more mass on the right side. And this buoyancy force will be acting, the new buoyancy force will be acting because of the tilt or because of the moment of the ship. So you keep in mind that one ship is there. So after giving some tilt, the buoyancy force of the buoyancy point will be shifting as per the submerging of the given mass. So right side mass is more, submerging of the body is more on the right side. So buoyancy force or the buoyancy point is shifting from B to B1. And force due to buoyancy is also shifted from B to B1 point in the upward direction, which is the resistance of the liquid. Now, because of this buoyancy force, what will happen? There will be a restoring couple generated about this BB dash. So BB dash distance, at a distance of BB dash, this force or the buoyancy force will be creating some couple, restoring couple, so that it is trying to bring back the body to the stable condition. That is one couple or one moment. One more couple is, see here, on the right side, what is happening? The triangular shape of the body. If you see the total 3D view, it is like this. The triangular shape of the front view is having the length L, height h on the opposite side of the theta, and x is the one side distance. See here, from the central axis O to the distance up to n, it is x. Okay, a small, whatever the volume they have considered or the area is considered, they have considered dx. But one side it is x. Opposite to theta, the height is h. How much it is immersed inside the liquid, that is h. Then the length, inside length of the given ship is L, that is given. Now due to this, what is happening? Extra mass is added after tilting to the right side. Extra mass is added to the body, or it is immersed in the liquid. What will happen? There will be small buoyancy force is added on the right side, and small buoyancy force dF will be neglected on the left side. Are you understanding? In neutral position, if you see, if you consider buoyancy point, it is Fb, and there is no buoyancy or the small buoyancy force is generated anywhere because it is neutral. But once you start tilting, or once you start changing the position, the mass of immersion of the given body on the right side or left side, according to this central axis, the mass which is immersed inside the liquid is going to change. So when mass is more on the right side, for example, you have taken right side, if immersion is more on the right side, what will happen? The extra buoyancy force is added because of the more mass which is immersed in the liquid. And here what is happening? This triangular wedge shape or the prism shape of the volume is lifted up. So that much buoyancy force is reduced. So these two buoyancy or small buoyancy forces are creating a couple about point O at a distance of x. And later we are going to equate these two couples. One moment is about FB and BB dash. One more moment is about O point due to this small buoyancy forces, that is dFB into x, dFB into x on the left side. So due to that couple of the preparation of the moment, what will happen? Those couples are trying to balance the body. And by the sketch I am telling, we know that B to M, as per sketch, is what? B to M is Vg plus Gm. That is, metacentric radius Bm is the sum of the distance between G to B, or buoyancy point to center of gravity, plus the metacentric height Gm, that we know from the sketch. Now we'll analyze how to write the couples about this O point and about B point. And later we are going to equate both the equations to find the metacentric height, that is Gm. So from this equation only we are writing Gm equal to. Any doubts up to this discussion? Have you understood how the small or extra buoyancy force is added and reduced on the left side, how it is added on the right side, and how a extra moment is generated due to change in the position of buoyancy point? Anything you want to add here? What about others? Have you understood the analysis of that sketch? How those forces and other distances are considered? Okay. So now we'll see how to write the moments about O point using the small buoyancy force added on the right side, and one more moment which is added on this right side because of buoyancy force shifting of the buoyancy point B1. Okay. So coming to the analysis, So here you can see, I can go for the geometry now. So we know theta angle, how much it is tilted here. The whatever the angle tilted here, theta, at the same angle, this triangular shape is going to immerse in the liquid. So we are considering both angles theta, and we know opposite and adjacent lengths. That is, we can write tan theta equal to, for the given prism shape. Means first we are writing the moment for this triangular shape prism. So this is like a prism. Front view is triangle, top view is like a rectangle, and entire volume, if you see, it is a prism. So in this theta, if you see, we know opposite edge is height, adjacent is x, and we don't know the hypotenuse here. So according to this, if I write, I can write tan theta, correct? So tan theta I can write as h by x. Then we can write it as height is equal to x theta. How much it is immersed? It is dependent on the width of that body from the center, or that radius of the body, x, and tilt of the angle theta. So I can write x tan theta, or for small angles we can take x theta itself. Okay, so this is for the triangular shape, wedge shape, or the wedge shape of the body, or it is like a prism. For that body we are taking how much extra part is immersed. And same for the area, if I take, I can write it as h into dx. How? Front view, if you write the area of this wedge shape, what they have written? They have written as h into dx. So for a small strip, what is considered here, red color strip, what is considered? For this small strip, if I consider area as dx is the width into height. This will be like a rectangular shape they have considered, small rectangular shape. Later they may integrate again. So that we already know. Whenever you consider small areas, later we have to integrate. So for small area dx, area is how much? Dx into h. In the front view. Similarly, for the top area, if you write for the same small strip, I can write small width dx and total length. Here they have not taken small length here. This strip is extended up to the total length of the prism. So I can write the area at the top side, it is L into dx. Top area, front area, and the height we have written. Now we can go for the volume. So slowly after volume we are going for the weight, then after weight we are going for the moment about some given distance from the center. Like that we are creating a moment, and for that moment these all details are required. So in this you can see total volume of the strip given. So strip means that small strip with dx distance, if you see, that we can write it as area into length, front area into length of the given body. So that we can write it as h into dx, front area, into length of the given body or a strip, that is L. So once again you can recall here volume for the small strip. If you recall the volume of this small strip for the entire prism, I can write it as dx into L into height, width into height into length. That will become volume of the small strip in red color. What is shown in the red color, it is the small strip volume. So this can be again substituted. So we already know the h value here. H we have written x theta for the triangular prism. So h I will replace here with x theta. Dx into L written as it is. So for the front side we are going to analyze now. Okay. So for this small strip we know the volume, which can be written either in height into dx into L. And for the substitution of theta, if you want to substitute theta, I can write it as x theta or x tan theta dx into L. Now we'll find out the weight of the wedge. So weight of the wedge on one side, because we need to find out how much buoyancy force is generated on this right side. See the triangular shape here in the front view. On this triangular shape, what is the buoyancy extra force is generated after extra immersing of this body? That DFB is the extra buoyancy force which is generated. That we are taking it as extra weight added on the right side. Because it is floating means weight of that body should be exactly matched with the buoyancy force also. So weight of this small strip should be balanced by that small extra buoyancy force also. So we are taking W equal to DFB. So now if you take the weight, how we are writing the weight? We are writing the weight by rho GB, rho G into volume. So for this purpose we need area, we need length, we need height, we need that angle. So different purposes there for writing all these distances, because we need volume here. Now in the front view, I can write the volume like x theta dx into L. So that volume I'll substitute here with rho G. That indicates total weight of the wedge added on the right side. So this addition is nothing but it is going to create some extra buoyancy force DFB. A small buoyancy force what is added, that we are writing it as DFB. Total buoyancy force what is available, that is capital FB. This is total FB at the bottom. This is also creating one couple here on the bottom side. Now weight is known or force is known because of the extra wedge shape on the right and left side. Now we can consider the couple or moment generated at the center point O. From the center, if you consider the couple what is generated, it is 2 times DFB into X. Why 2 times? Because it is on left and right side, both sides. Both sides the moment will be generated. That's why we are taking 2 times. So again substitute that rho G x theta dx into L into 2x. So here dx we can replace later by integrating. In this we know the dx into L is the top area. So I can substitute as dA, which is representing here top area, not the front area, top area. I can write it as again rho G theta into 2x square, 2x into x, 2x square. Okay, dx into L, whatever is there, the term here, that you have to recall from this words. Dx into L is the top area of the strip. So I'll write dA. Okay. So once this is done, now we can integrate, because here we want to replace that dA term, small dA, because dA we have taken for the dx width, not for the total x. So we need to integrate that. So integrating this moment of couple, we can write it as rho G theta into 2 integration of x square for the given limits from 0 to total x into dA. So 0 to x, if you integrate x square, what will happen? It will be full x or x minus 0. But here x square is there, but the meaning, it is the moment of inertia or integration of distance square into area. So whenever if you do that, we are going to write it as moment of inertia itself. So 2 times integration of x square dA, we can replace the entire term as moment of inertia I. So I can write it as rho G theta into I. This is one of the couple generated because of the triangular wedge shape immersion on the right side and triangular wedge shape body which is taken above the water surface. So due to this change in the masses on the right and left side, there is a couple generated about this point O. So that we can write it as moment of couple about O as rho g theta into moment of inertia. So this will call it as equation number 1, because as I told you, we are finding moments about O and we are equating moments about B. Both should be equal because these two small buoyancy force what is generated at dx and the total buoyancy force what is displaced from the central axis, both are trying to restore the body. Okay. So one more couple will write or moment. So moment due to this total buoyancy force. The total buoyancy force is what? It is acting from B to B dash or B to B1. FB into B to B1 is a moment acting about B. Now we'll analyze how to write B1 in terms of these areas L, H, X or theta. In terms of that, how to write. So B dash, if you see, it creates one more triangle here. See, B dash and M is a triangle which makes theta angle. So again we'll go back to theta. Again we'll substitute all the dimensions given there in the sketch, and again we'll equate with the common terms. So what I'll do here, I will write moment about point B, which is generated is total buoyancy force FB into distance B dash. And as I told you in earlier classes also, in earlier analysis also, whatever the force of buoyancy generated and the body is floating, that is nothing but is equal to weight of the given immersed body. So that weight of the total body we have taken, or total weight of the body is taken, and BB1. So BB1 triangle, if you analyze, I can write opposite by adjacent again, because in the triangle we know only two sides. Here, opposite B dash we know, adjacent is MB. We don't know B to M because there is no any other dimensions. But we know some relation between GM and BM. Some relation is there between the center of gravity, metacentric heights. So you can write tan theta. Opposite side is B dash, the metacentric point. So again for small angles, we can write B dash equal to BM theta. Okay. So now we found out one of the moment, that is W into B dash, I can write it as BM theta. So W BM theta is the couple generated about the point B, and that we can call it as equation number 2. So these two moments now we are going to equate. So both equations are in terms of theta now, common terms. Now after equating, we are finding BM value. So once you equate these two terms, I can cancel theta. BM I can write it as what I can write, the sum of GM plus BG as per the given sketch. That is, in this plus metacentric radius, sorry, BG to GM, that gives metacentric radius BM. So that is written here. BG plus GM, W is taken on the right side. So this will be rho G I by W. Now rho G and W we know some relation. What is that? W can be written as rho GB. Okay. W is rho GB. And I can replace this rho G by W as W by rho G itself. W by rho G is volume. So I can write it as GM equal to, here GM equal to moment of inertia I. Which moment of inertia? See here. Be very careful. Moment of inertia of the given surface. Okay. Or the top area. Top area moment of inertia. That you have to consider. Not the front area. Because here see dA is the top area. dx into L. Top area. Top area moment of inertia you have to consider. Moment of inertia for the front view. Only from the moment of inertia. So finally what we can do now? Now we can tell the metacentric height G to M or center of gravity to center of metacenter point, center of gravity to metacenter point is given by ratio of moment of inertia on the top surface to the volume which is submerged minus distance between buoyancy point to the center of gravity. So this equation all of you note down carefully. And in between equation whatever you have written here may be useful in some of the problems where some of the direct values may not be given. Like I naught may not be given, you have to go by moment of inertia equation directly. If volume is not given, you can go by this rho g by w or w by rho g, you can find out volume. If bg is not given, you can go by this or this equation, main equation. If bg is not given, I can find out by metacentric height and metacentric radius. Like one can find out bg. All of you understood the steps? Explain. Or is it enough? Repetition is not required, no? Okay. So once again we'll see the derivation. So to find the metacentric height gm, see here, this gm we need to find out metacentric height. And generally we know the equation bg plus gm. Okay, that is one part. Now, initially given body which is floating on the given surface of water, like a ship. You see on ship, this is the ship, front view and top view. And any tilt is given. Okay, at this axis, about this axis, if I rotate it towards right side or left side, it will try to create some restoring couple and it will try to come back to the original position. So that stability of the body is maintained and it will continue to float on the given liquid surfaces. For that, the front view of this sketch, if you see, just zoom here. Yes, here, if you see this tilting of the body in the front view, the right side tilt, once you do it, what will happen? This body will be submerging. This part of the body in triangular shape, see here, triangular shape, it is submerged. Other side, what is happening? This amount of mass of the body is lifted up, means buoyancy force will be reduced here. Here buoyancy force is added, dFb is added. It is acting on upper side, it will be acting on the lower side because of the lowering of the buoyancy force. Similarly, the central axis what we have considered earlier in the original shape, after tilting, what is happening? The more mass is added to the right side because of the submerging. Less weight or the less mass is inside the water on the left side. That's why what will happen? The buoyancy force point will be shifted from B to B1 on the right side. If it is tilted left side, B1 will be on the left side. Just a mirror image. So what is happening here? Because of this shifting of B1, the force due to buoyancy is acting at this point. And due to change in the positions, see here, earlier both the forces, the weight of the body and the buoyancy force, both are acting on the same line. But here now it is shifted. Weight of the body is acting at G point, or it may be shifted to in between. And here buoyancy force is acting on this line. So due to this shift, what is happening? There is a moment generated at the bottom. This moment is FB into BB1. This we can also write it as in terms of theta. What is that BB dash? We can write BM theta. In terms of tan theta, if you take tan theta is BB dash by BM. So BB dash equal to B1. It can be written as BM into theta for small angles. That is one couple. One more couple, what we need to find out is because of this volume, how much it is H into L, where small width dx, height is h, L is total length in the top side. You can see the length. Front you cannot see the length. So that length should be multiplied. That will become the volume of the strip, small strip. Then later you can integrate. Once you in this, what relation we know in terms of theta, because couple also we have taken in theta, you can write first equation as FB into BB dash, first equation in terms of theta. Then later in the front view, I can write this volume of the given body and couple generated. Couple means what? I need to know how much is the extra buoyancy force is added here. DFB is nothing but the extra weight, how much it is added. It's nothing but DFB into the distance between the fixed point or the axis of rotation. That is O. From the O, if you consider it is at a distance of x. So I can write DFB into x for the right side. On the left side, one more couple is there in the opposite direction. That is DFB into x. So totally, how I can write? I can write 2 into DFB into x. Is that clear? And with volume, because we need to go for the total weight. Total weight can be given with volume. So that is shown here in this here. Okay, volume is how much? Volume is x theta dx into L. So in terms of theta, they are written. In terms of normal volume you want to write, you can write it as what you can write x theta as h here. X theta is h, you can write h into dx into L. That is also one of the volume of the given strip. So h only what they have done, they have replaced with x theta. Now we need to find the moment. So moment, as I told, it can be written as 2 times x into dfb. So 2 times dfb. Dfb is what? Weight of the body itself. Weight is rho g v. So rho g v is x theta dx into L. So in this, what I can write is 2x square I can write directly. Dx will be retained as it is, or dx into L is top area. You can write area at top or dA small area at the top. Then you can integrate. After integration, this equation can consider for couple. See here, rho g theta, integration of this 2 into x square dA. If you consider, this is nothing but moment of inertia on the top surface. Just a minute. Yes. So once you write these two moments, like now I'll call this equation as 2. Earlier we written equation this as 1 now. In this next one more type of explanation. So these two equations, I will take rho g theta moment of w into bm theta, because b dash we have replaced with bm into theta for the small inclinations. Tan theta we have
Sir,
replaced with
sir,
theta.
zoom out, sir.
Yes, zoom more. Okay. Screen is visible to all. Okay. So here you can see, once we equate these two moments about O and about B, what we are writing? We are equating rho g theta I equal to common in both the terms, so theta can be cancelled. So without difference between buoyancy point to the metacentric point is written as Bg plus Gm. Okay. So from this Gm, what I can do is I can write rho g minus Bg, and in this you can keep as it is rho g by W, or what I can do is I know W as rho gb and by rho g in opposite type, I can write it as 1 by V, because V is W by rho g here. So I have written I naught divided by volume, or 1 by volume into I naught minus Bg. So this gives the main equation for the metacentric height, that is Gm equal to I naught by V minus Bg. So all of you note down these two equations, or what are the equations required for you can note down. Bm equal to Bg plus Gm, this you can note down. Then you can note down this also, tan theta, because some examples maybe theta we need to find out for finding some h value. So in such cases we need theta also. Then h as a height, x as the distance or the width. So tan theta in front of you right now. And one more theta is here from the total buoyancy force what is shifted here at B1. For this, one more theta we are writing like this. Tan theta is B dash by Bm. So anytime if theta value is required, you can find out some of the distance B dash, or Bm also you can find out. Bm equal to B dash by theta, like that in numericals. So these derivations are nothing but theoretical or the equations which you can use for the n number of problems. So we'll see the one problem. The question we'll understand. We'll stop the class. In next class, we'll solve the problem. How to understand it. Yes, derivation you have to write completely. We may not show all the sketches. This sketch you can show, only front view. See, this sketch may not be important because only for to total length I'm showing here, or how it is a prism I'm showing here. This sketch is important. The front view with the tilting force. This front view you have to draw, or this sketch is important. With this one sketch, you can derive the equation. Okay, anyway, another 4 minutes are remaining. We'll take the problems and the solution in the next class. Send already notes is in the classroom. After I have sent the notes in the classroom already. And one more thing for the coming IA test. For the upcoming IA test, the syllabus is up to pressure measurement and manometers. Okay, up to that, the syllabus is there. Just a minute, I'll show the syllabus. Yes, Ashish and Akhtar, notes up to this metacentre, you find it in the stream. Okay, you scroll down all the messages. Or in the I have added the notes up to the metacentric height. Also, you have to refer books, not only notes, you also refer the books. Like Bansal is there, or the Rajput is there. Okay, you can refer the books and you can for the coming IA test, properties of fluids. Okay, first chapter, and pressure measurement, hydrostatic law and Pascal's law. These things are very important. And even some small phenomena like capillarity or vapor pressure, surface tension. So those things are very important. Yes. That syllabus here. Unit 1, basic properties of the fluid. Unit 2, fluid statistics with Pascal's law, hydrostatic law. Then pressure measurement with the gauge and absolute pressure. Manometers, total pressure force and the center of pressure. So I think we can keep up to this pressure measurement and location of the pressure. Okay, for the submerged surfaces. So up to here, the syllabus is there for the IA test. So from buoyancy, we'll keep it for the second IA test. Okay. Notes are not sent in classroom. Only first unit is notes sent. Only first one minute. All can see the screen. Okay. Just watch this. How much syllabus is there, or not? So much I was shared. Will just observe. See here, this is the second chapter, pressure measurement. Only module 1 is written. Half of the second module is also there. See here, pressure measurement with respect to gauge pressure and atmospheric pressure, absolute pressure. This is there. Manometers are there. This is in the second chapter only, second unit. Okay, up to here it is there. So today I'll share this file. This file I'll share. Okay, I'll share now itself. Wait. Module 1. Okay. Module 2. Okay, I will split that file and separately module 2 I'll prepare and send it. Okay, after splitting that PDF. Okay, thank you. Yes. Any other doubts regarding IA test? Okay, I'll stop the class. On Monday, we'll take the problems on metacentric height. I think from Monday you have IA test. If classes are there, we'll take the class. Otherwise, next week.